So many of the techniques that are used to estimate percent body fat calculate body density, and then we can convert that body density into percent body fat. So when we talk about body density, I think it's important to understand what we're talking about. So density of the body is just your body mass, which is your weight, and then it's divided by your body volume. So body mass is actually relatively easy to get. All you need is a scale, so it's basically your body weight. What's more challenging to obtain is your body volume. So that's what these techniques are after. And then once you have volume, you can estimate body density. And then there are several equations that you can use to convert body density into percent body fat. So the most common equation used to convert body density into body fat is the Seary equation. So the Seary equation is going to assume the following. That the density of fat is about 0.9, density of fat-free mass is about 1.1, assuming water has a density of 1 gram per milliliter, and that's at a given temperature. And so we can see that fat-free mass is more dense than water, so it's going to sink. So that's going to help us when we use the technique of hydrostatic weighing. And fat is less dense than water, so it tends to float, and we'll see that how that plays into hydrostatic weighing also. So interestingly enough, these assumptions are not true for all populations. So there are other equations, like I was saying, there's many equations to convert body density into percent body fat. It's just the Seary is the classic one used, and it's the most common one used, but there are other more population-specific equations for different ethnic groups and male versus female also. So starting with hydrostatic weighing, the error associated with hydrostatic weighing is about 2.5%, which is actually pretty good when you think about it. So anytime you get below around 3% error, and as far as percent body fat estimation, it's considered to be pretty good. So hydrostatic weighing is based on Archimedes' principle, which basically says that if you put an object in water, it's going to be pushed up by a force equal to the volume of water that is displaced. So in other words, if you get in a pool of water, there's some force acting on you, pushing you up. That force is proportional to the amount of water that your body is displacing. So in other words, if we can calculate how much force is pushing up on someone underwater, it gives us an idea of what the volume of that person's body is. So in other words, loss of weight of the subject when completely submerged. So you weigh so much on land, you get in underwater, you're going to weigh a lot less. And you consider that difference, and that's going to be proportional to the volume of water displaced, which is basically going to be the volume of your body. So in this technique, you measure your body weight in air, body weight underwater, and we use that to estimate body density. So when we do this technique, I'll show you a picture, and you may see this in the lab also. You weigh someone obviously on land on a regular scale, and then they have to be weighed underwater. They have to be completely submerged, and when they're underwater, they have to exhale as much air as they possibly can, because the air in their lungs could help make them lighter, and that could affect the results. So we want them to exhale as much as possible where only the residual volume is left in the lungs. And then we account for the residual volume by either measuring it or estimating it, which is more commonly done. We also have to consider the air that might be in the gastrointestinal tract. That's really hard to measure, so we usually just estimate it at about 100 milliliters. So we put all of this in an equation, we get body density. This is what that equation looks like. So body weight in air divided by the loss of body weight when you go underwater, minus the residual volume minus the gastrointestinal air, which we assume to be 100 milliliters. And the water density comes into play also because that can affect your weight, because it affects the water density. So water density is, we said earlier, is about 1, but it depends on the temperature. So if you do this test in the lab, you're going to have to measure the water temperature, and then actually find the water density at that given temperature. So this is what it looks like. The person's trying to go underwater. Ideally, they would be completely submerged, and their body weight is obtained via a scale. And then once you have that density, you just convert body density to percent body fat using the Siri equation or a similar equation. So this is the Siri equation, and no need to memorize this equation, but this is it. This is the most commonly used equation. But there's others, like I said. This is another example. And you can see they're all similar. They just have different constants. So depending on what individual you're looking at, if they are of a certain ethnic group, or male versus female, there'll be a specific equation for them. The next technique I wanted to cover is air displacement plethysmography. This is a similar concept in that you're trying to get the volume of the body to get density, but this time we use how much air is displaced. So the major technique that uses this technique is the BodyComp. So the BodyComp, if you've seen it, looks like a little oval shaped structure, but the air is pretty good, so right around 3% on average. Correlates well with hydrostatic weighing. So similar concept, but you sit in a chamber and the volume of air displaced is measured. From that, you can get body density. So we know mass, we get volume, then we can get density. But then we can use the Siri equation or something similar to convert percent to percent body fat. So this is what the BodyComp looks like, and it's just an air chamber. So additionally, we can use skin folds. So skin folds is one of the more popular techniques in laboratories because it's very cost effective. So we use skin fold calipers to measure skin fold thickness at various sites. So the big assumption here is that subcutaneous fat that we mentioned earlier is representative of total body fat. And the air is about 3.5% when it's done correctly. So when you have a trained technician doing the measurements, the air is pretty good. The problem with skin folds comes when you get somebody who's not used to doing it and they're not competent in it, and they are all over the place with their measurements, and then the error goes way up. So this error is assuming that the tester is competent and they're experienced and they know what they're doing. So we can use a 3, a 4, or 7 site measurement. So obviously the more sites that you assess, the better, the more accurate it's going to be. And then again, we put the sum of the skin folds into an equation, and that's going to give us body density. The equations that we put the sum of skin folds into take into account sex and age, and then that is going to give us density, and then we can use the Siri equation or something similar to convert that density to percent body fat. Bioelectrical impedance. In this technique, a small electric current is passed through the body, and impedance basically means resistance to flow. So in other words, as this current is flowing through the body, that electricity is going to meet some resistance. So this is based on the assumption that the fat-free mass of the body is a better conductor of electricity than fat. So the quicker that electricity flows through the body, the less body fat it's going to say that you have. So air, a little bit higher. There are a lot of different ways to do bioelectrical impedance. There's scales, there's handheld devices, and then there's more laboratory-based systems. So the air here is really more of a laboratory-based system. So some of the bioelectrical impedance devices that you can find for relatively cheap in the stores, the air may actually be a little bit higher. So, but these are heavily influenced by hydration status and temperature, because the amount of water in your body is going to affect the impedance, the flow through the body, and also temperature can affect it. So this is what some of the devices look like. This would be more of the laboratory-based bioelectrical impedance, and then this might be something you see at a gym, where handheld, that these little sensors are conducting the current, and same standing on a scale. Relatively easy technique, but again, the air is a little bit higher than what you get with some of the more established techniques. All right, then we have DEXA, dual energy X-ray absorptiometry. So in this technique, an X-ray scan is taken of the body, and then a technician goes back and analyzes that scan and can see he or she can see what's fat and what's not. So you can see a lot of different tissues. So this is thought to be the most accurate at the moment. So air, about 1.8%, correlates well with hydrostatic weighing again. So likely the most accurate. Classically, hydrostatic weighing was thought to be the most accurate technique to assess percent body fat. But now with the use of DEXA is supposed to be a little bit better. So problem is relatively expensive. This is what it looks like. So person lies down, a scan is taken of the body, and you get a scan like this. A technician goes in and actually assesses how much fat the person has. And the good thing about this, as you can see, you can examine fat in different regions of the body. So this would be an example of a scan and the printout that you get. So a good thing about DEXA is you also get bone mineral density, and that's really what DEXA kind of originated for, to see how much mass is in your bones to screen for osteoporosis. So that's a good thing that you get also, but you additionally get percent fat. So you can see by region of the body even what the percent fat is. All right, so those are the major techniques to estimate percent body fat. And so I have a few other topics I want to cover. And one of them is just weight management, some key factors to consider. So most individuals kind of refer to the energy balance equation when you think about weight management, basically calories in, calories out. Not everybody completely agrees that this is the best way to target weight loss, but nevertheless, it's relatively straightforward. It assumes that if you intake more energy than you expend, you're going to gain weight. If you expend more than you intake, you're going to lose weight. So relatively simple concept. So intake more than you expend, gain weight. Intake less than you expend, lose weight. So ideally, using this equation, you can see that if you want to lose weight, you would want to eat less and expend more energy, and you could do that by exercising more. So as far as losing weight, body weight, if you want to lose a pound of fat, it's equivalent to about 3,500 calories. So you'd want to have an energy deficit of about 3,500 calories to expect to lose 1 pound of body fat. So general recommendations, what's recommended is not too much weight all at once, so about 1 to 2 pounds per week. Negative energy balance of 500 to 1,000 kcals per day. If you think about this, an easy way to do this would be to reduce what you're intaking and also increase what you're expending. So if you wanted to have a negative energy balance of 500 kcals per day, you could do 250 calories of physical activity more than what you're doing now, and then eat 250 calories less. So when you think about it like that, it's not as daunting as if you were to say, all right, I have to expend 1,000 more calories in physical activity. So no crash diet, so 1,200 calories would be the minimum that you would want to intake each day. Combination of diet and exercise, like I was referring to, and then kind of a good goal is about 2,000 kcals per week in physical activity. So there's this set point model that I wanted to bring up, and this is brought up a lot when you talk about weight loss. So the brain is thought to set your body weight when you talk about this set point theory. So the hypothalamus controls our feelings of hunger and thirst. So it's thought that this hypothalamus kind of sets our body weight because it's going to tell us when we're hungry and when we're not. So ideally, if your set point was set at a manner to where it encouraged you to be hungry all the time and you were eating a lot, then ideally you would want to change that set point. So this is debatable whether or not you can truly change that set point, but there is some evidence that diet and exercise can alter that set point over the long term. So is there a genetic component to weight loss and obesity? So yes, there's definitely some evidence that there's a genetic component to obesity, but it's not thought to be the only thing at play. So in other words, if you have a family history of being obese, even though you may be predispositioned to be obese, there's no reason that you would have to be. So it plays a relatively minor role in the grand scheme of things. So about 25% is what is thought to be the genetic component to obesity. So how does genetics play a role? It can influence how much spontaneous physical activity you're doing. So that would be like, if you just think about it, some people are just natural movers. They just always want to be moving, whereas other people just kind of want to sit around. There's a genetic component to that. Resting metabolic rate. If you genetically have a high resting metabolic rate, you're always going to be expending more calories, less likely to become obese, and vice versa. Thermic effect of food. So in other words, how your body metabolizes food and the energy expenditure that goes along with that. That can be genetically determined. And then also our usage of nutrients, carbohydrate and fat. Some of that has a genetic component to it. So we're going to do a few practical calculations here to, give you some ideas on how you can use some of this body fat information to come up with, to be useful and practical. So first thing I want to do is relatively simple, calculate fat and fat-free mass. So if you had a 200-pound person with 30% fat and you wanted to know how much fat mass they had, you would just multiply 200 by 0.3, and that's 60 pounds. So a 200-pound person with 30% fat has 60 pounds of fat. And then how much fat-free mass do they have? Well, we just subtract the 60 from the 200. We're going to assume if it's not fat, it's fat-free mass. So that would be 140. So make sure you can do that simple calculation, calculating fat and fat-free mass. Another practical use of this information is this example. And this is a little more detailed, but I want to talk through it and some of the usefulness of doing this. So in this example, if somebody weighs a certain weight, in this case 90 kilograms, and they're 20% body fat, and they have a target percent body fat. So if they want to get down to a body fat of, let's say, 15%, how much weight would they need to lose? Or how much fat weight, I should say, would they need to lose? So assuming fat-free mass is unchanged, how much fat weight will they need to lose? So we're making a big assumption here that if they lose weight, all of the weight they lose is going to be fat. That may or may not be true. So it's probably not 100% true, but hopefully most of the weight that they're losing is fat mass. So we like to think that the bulk of this is accurate. So nevertheless, let's work this out and see how to do this. So the first thing we need to know is fat-free mass. So if they're 90 kilograms and they're 20% body fat, 90 times 0.2 is 18. That means they have 18 kilograms of fat, and then that means their fat-free mass is 72. So if you subtract out the 18, which is fat, everything else, assuming everything else is fat-free mass, it gives us 72 kilograms as the fat-free mass. Alternatively, you can just, if you know he's 20%, he or she is 20% fat, that is, we assume is 80% fat-free mass. So you could just go ahead and do the 90 times 0.8, and you still get 72. So regardless, 72 kilograms is the fat-free mass. If the desired fat mass is 15%, which would be a fat-free mass of 85%, we're going to assume, remember, we're assuming this fat-free mass doesn't change, that the person is only losing fat mass. So we would set this up like this: 0.85, which would be their fat-free mass, times the weight that they're trying to get to, should equal 72. So remember, fat-free mass is 72 kilograms. We're saying it's not going to change. And with their new percent body fat, they're going to have 85% fat-free mass. So if we multiply that times the target body weight, we should get 72. All right, so this is what we're looking for, this target body weight. So if we just rearrange the variables and do some algebra, target body weight equals 72 divided by 0.85. We divide 72 by 0.85, I get 84.7. So that 84.7 represents what weight they need to get to have a 15% body fat. Again, that's assuming that fat-free mass doesn't change. So that is, if that's their target body weight, then 90 minus that is how much weight they need to lose. So this person, to get down to 15% body fat, would need to lose approximately 5.3 kilograms of weight. And so, relating that to pounds, about 11.7, so almost 12 pounds of fat. Again, that gives you an idea of how much weight you need to lose to reach that target. It is assuming, and I'll say it again, that you're only losing fat mass. Ideally, that's the case, but in reality, it may not be 100% the case. Nevertheless, it gives you an idea of how much weight you should lose or need to lose to reach a certain target body fat. All right, another example, which is a little more clear, I think. If you wanted to lose a certain amount of weight over a certain period of time, how much energy deficit would you need each day? That's an important thing to consider. If you have a goal of losing a certain amount of weight over weeks or months, it helps to break it down day by day to see exactly what you need to be doing each day to reach these long-term goals. So this example, I put 4 pounds of fat over 2 months. So let's assume 2 months, 30 days in a month, so 60 days. And if we know that approximately 3,500 kcals is 1 pound of fat, we can work this out. So 4 times 3,500, it's 14,000 kcals. That's how many kcals need to be expended to lose 4 pounds of fat. It sounds like a lot, but when you break it down over the long period of time that we're talking about, 2 months, assuming that's 60 days, then 14,000 divided by 60 is 233 kcals per day. So when you look at it like that, it doesn't seem that daunting. So 233, that's the energy deficit each day. So again, that could be expending 233 more calories each day, or intaking 233 less calories per day, or a combination of both. Ideally, a combination of both would be the best case scenario. All right, another example which takes some other things into account. If your body weight is 70 kilograms and you want to expend 250 kcals per session that lasts 30 minutes, what intensity do you need to work out at? So this takes into account some of those other calculations we did earlier in the semester. So this tells us how many kcals you need to be expending per minute. So 250 kcals per session. That's what you want to expend. You want to work out for 30 minutes. So that means you need to be expending 8.33 kcals per minute. To determine what intensity that is, as far as VO2 or METs, so we take that and we use the caloric equivalent. We use 5 just because that's the standard one. So 8.33 times 1 liter of oxygen for 5 kcals. Get a VO2 of 1.66 liters per minute. So that's the VO2 associated with that. If we convert that to relative VO2, that's a relative VO2 of 23.8. That's just doing that conversion we did earlier in the semester, converting absolute to relative VO2. And then we could report this in METs, just dividing by 3.5, 6.8 METs. So given this example, the person would need to be exercising at approximately 7 METs, and that would allow them to expend 250 kcals in 30 minutes.